Welcome to this deep dive. As part of our ongoing series for number theory students exploring the OEIS, today we're tackling sequence A000215.
Ah, yes, the Fermat numbers.
Exactly. Defined by that, well, really elegant formula, full 10, plus 210 plus 11. They're a fantastic way into some really deep number theory ideas, I think.
They really are. It looks so simple,
Yeah.
210 plus 11, but the amount of mathematics it's generated is quite remarkable, still fascinating.
Right. So the first few are 3, 5, 17, 257, 6, 5, 5, 3, 7. And looking at those, Pierre de Fermat back in the 17th century, he guessed, didn't he? He conjectured that all numbers from this formula would be prime.
A very natural conjecture to make, seeing that sequence. 3, 5, 17,
Yeah.
they're all prime.
Seemed like a solid pattern. But, well, as we'll get into, the story isn't quite that straightforward.
Not at all.
And to help us unpack all of this, we're very fortunate to have a Fields medal-winning mathematician with us today. Welcome.
It's a real pleasure to be here. Fermat numbers, they're just a classic example, really. How simple formulas can lead you down some very, very deep and tricky paths.
Okay, so let's maybe start with some of the basics. The patterns within the numbers themselves. There are these recursive definitions, aren't there?
Yes, several interesting ones. They give different perspectives on how the numbers grow.
Like a funim-1, 112 plus 11, That's for 1-1.
That's one, yes. It shows how each one sort of squares up from the previous one, roughly speaking. Then there's 101 times F1 times dots times M1 plus 22, also for 1-1.
Ah, that one's really, it connects each number to all the ones before it.
It does, and it's incredibly useful. It highlights the structure.
And there are others, too. I think I saw 100 plus 201, 2 dots, below 0, 2.
That's another one, yes. And if
Yeah,
101, M12 for 1-2, they all reveal different aspects of this internal structure and just how fast these numbers grow.
That rapid growth, it leads to something quite striking about their factors, doesn't it? Goldbach's theorem. Not the conjecture everyone knows, but a different one.
Right, related to Christian Goldbach. It states that any two distinct Fermat numbers are coprime. They don't share any common factor greater than 1.
Okay, so how does that work?
Well, it hinges beautifully on that second recurrence relation we mentioned. 5n CDOX, 5 and 1 plus 2, 2. Suppose you have two Fermat numbers, 5i and $5, with AJ jaw. And let's assume they share a common factor, call it A, where AJ jaw 1.
Okay.
So A divides $5.
Yeah.
Now look at the formula for $5. Since AJ jaw, stuff all the terms in that product, cotox FJ1. So A must also divide that whole product.
Right, because it divides one of the factors.
Exactly. But then A must also divide the difference between $5 and the add product. And what's the difference?
Just 2.
From the formula. Just 2. So A must divide 2. But all Fermat numbers, 5 or I for $1 are odd. $2 is always even. So adding 1 makes it odd.
So A can't be 2.
Yeah.
And it has to be greater than 1.
And it has to be odd because it divides an odd Fermat number.
Yeah.
So it can't divide 2. That's the contradiction. It must be pairwise coprime.
That's very elegant. And this coprime property, it has that amazing consequence, doesn't it? Another proof for the infinitude of primes.
It does, yes. It's a lovely argument. Just pick one prime factor, say PD dollars, for each Fermat number for quartilars. Since all the phi dollars are pairwise coprime, all these chosen prime factors, T dollars, P1, P2, dots, must be distinct.
So you have an infinite sequence of distinct prime numbers right there.
Precisely. A beautiful connection.
Are there other sort of basic properties? I remember reading something about the last digit.
Yes, a small curiosity. If you look at the decimal representations, apart from phi dollars and 3 and 35, every other Fermat number, full rolls for in dollars, 1 do ends in the digit 7.
Really? Why 7?
It comes down to the powers of 2 modulo 10. The exponent is $2 for $1, quarter is multiples of 4, $2 293, 3 souls 16 $16. And $2 raised to a power that's a multiple of 4 always ends in the digit 6, like 24, 16, 28, 2, 85, 6, 16, etc. So 2 ends in 6 for the 1.
And $6 plus 1 equals 17. Okay, that makes sense.
A neat little pattern. And there's one more property worth mentioning. Perhaps Solomon Galam showed in 1963 that the sum of the reciprocals, 1f dollars plus 1f1 plus 1f2 plus dots, adds up to an irrational number.
So not a simple fraction. Interesting. It connects them to, well, a different class of numbers entirely.
It does. It just hints at the depth hidden in this sequence.
Okay, so some really nice structural properties. But the main event, historically speaking, is really about their primality, isn't it? Fermat's original idea.
Absolutely. That's where the main story unfolds. And Fermat was right about the first few. F3, F1, 5, 2277, Zen, F3, 25777, and 4655376 out. These 5 are indeed prime numbers. We call them Fermat primes.
And famously, these are the only ones we know, right?
That is correct. Still, after nearly 400 years, those are the only confirmed Fermat primes. Fermat himself believed the pattern continued.
But it didn't.
No,
Yeah.
the very next one, 5 psi y,
Yeah.
turned out to be composite. It was Leonhard Euler in 1732 who showed this.
Euler again. And he found the factor, didn't he? 641.
Yes. He calculated 5 dollars, which is 2 to the left of 1, or 4,294,967,297. And he found it equals 641,477 evotters.
That must have been quite a shock, overturning Fermat's conjecture like that. It shows you can't just rely on the first few terms of a sequence.
A classic lesson in mathematics. And Euler did more than just factor 5 dollars. He proved a crucial theorem about the form of any potential prime factor, a Fermat number, $4.22.
Oh, what kind of form?
He showed any prime factor must be of the form 2 lambs plus 1 plus dollars for some integer counter. This was later improved slightly by Lucas to k out to 2n's plus 2 plus dollars.
So for $5, the factors must be of the form 2n plus dollars plus 2 plus dollars, which is $5, 2 plus 7, 1, which is Cham at 128 plus dollars.
1 plus 2 covers by dollars plus 2 plus the law ensemble, or k out 128 plus 1 is, yeah.
Let's check 641. Is it like that? 641 mamos is 5 times 128 plus the law. Yes, it is. 25 Lars. That's amazing. It really restricts the search.
It does significantly. It tells you not just any prime can be a factor.
Can we see quickly why 641 divides 5 dollars? I know modular arithmetic is involved.
Yes, it's a rather neat argument. The trick is to notice two things about 641. First, 641.2 equal 5 times 27 plus a 1 point. And second, 641 twos plus 24 2.
Okay.
From the first equation, $5 times 27 equiv make 1 p1 is 641.
Right, just rearranging.
Now, raise both sides to the fourth power. You get $5 times 27, 4 p1 640, so $54 times 2 1 p1.
Okay, following so far.
Now, use the second equation, $641 plus $24. This means $54 and $24. This means $54 equiv 1 p1 641.
Ah, substitute that in.
Exactly.
Yeah.
Substitute $244 for $544 in the congruence we just got.
So
$24 does 2 equivalent.
which is 241 p.
For $200.41.
F55 is 2 plus L1, so 5 Lars for P1 and 420.
Precisely. It shows 641 must be a factor. It's elegant.
It really is. Okay, so Euler blew Fermat's original idea out of the water with $4. What are the big questions now? What don't we know?
Oh, several fundamental ones remain wide open. Maybe the biggest is a Dothan composite for all $1,444? It seems likely, given the evidence, but we have no proof.
So maybe there are only 5 Fermat primes in total.
That's the conjecture many people lean towards, yes. But proving it seems incredibly hard. The flip side is the question posed by Eisenstein back in 1844. Are there infinitely many Fermat primes? We simply don't know. It could be finite, it could be infinite.
And what about composites? Are there infinitely many composite Fermat numbers?
Also unknown. Though, again, it seems likely there are. And there's a more technical question. Is every Fermat number square-free? Meaning, does it have any repeated prime factors? Like P Tauler 2.
Does it seem like they are square-free?
Yes, all known factorizations are square-free. It's conjectured they all are, but again, no proof.
It's incredible that these basic questions are still unanswered after centuries. So what do we know beyond a $5? How far have you checked?
Well, we know for sure that a $5 is composite for all non-allowers from 5 up to 32. That's a solid block.
All composites in that range. But do we know their factors?
That's the challenge. We only have complete prime factorizations up to 5. That's right. For the numbers after that, we might know some factors, often quite large ones, but not necessarily all of them. And for two values, $1, $2, and $204, we actually know they are composite, but we haven't found a single prime factor for either of them yet.
That's amazing. We know they're not prime, but can't find the pieces.
Exactly. It just shows the scale of the difficulty.
Yeah.
These numbers get astronomically large, incredibly fast.
What's the largest one known to be composite?
The current record holder, I believe, is $17,233,954. A factor for it was found in October 2020. The factor itself is $7, not $218,233,956 plus lower. Just imagine the size of F18,233,954 itself.
Mind-boggling. Okay, so finding factors is clearly hard. How do people even test if these huge numbers are prime or composite in the first place?
There are specific tests that work well for numbers of this form. The most famous one is Pepin's test, developed in the 19th century.
Pepin's test, how does that work?
For Aston dollars, Pepin's test states that $7 is prime if and only if 33 vols raised to the power, Fn1 to Sn2, is congruent to $1 modulo phobanaton on 10th and 2, $2 equivalent to 110 cell.
If and only if. So it works both ways. It can prove primality.
Yes, that's the beauty of it. It's a deterministic primality test specifically for Fermat numbers. It doesn't require trying to find factors.
But that exponent, 1 bol 2, that's enormous. Isn't that calculation still incredibly hard?
It is computationally very intensive, yes. You're doing modular exponentiation with an exponent that's roughly half the size of Fourier itself, and the modulus is 5n. While it's technically polynomial time relative to the logarithm of 5 alone is, which is related to 2L of EM, the actual numbers involved are immense. It quickly becomes infeasible.
Right. So useful in theory, but hits a practical wall pretty fast. Is this related to Proth's theorem?
It is, yes. Proth's theorem is a more general test for numbers of the form 1 2 meters plus $1, where colors add and 2 needle dollars. Pepin's test is essentially a special case of Proth's theorem applied to 1 Nagel 1 plus Lellers using the base and 3 Lauer.
Okay. And these tests, if the congruence fails, they tell you it's composite.
Correct. If $3 FN1 $2 is not congruent to $1 pan Maupai, then Venturi is definitely composite. But crucially, the test doesn't tell you what the factors are.
Just that it has factors. Finding them is the next harder step.
Exactly.
So what methods are used for that? For the actual factorization attempts?
Well, given the size, specialized algorithms are needed. The elliptic curve method, or ECM, is particularly good at finding relatively small prime factors.
Okay.
And for the really massive searches, there's a large distributed computing project called Fermat Search. It uses the idle processing power of thousands of volunteers' computers around the world to look for factors.
That's fantastic. Like SETI at home, but for number theory?
Precisely. It's a major collaborative effort, a great example of citizen science.
So what's the current score then? How many factors found?
As we said, complete factorizations are known up to 5 $.
Yeah.
As of late 2024, I believe the total count is something like 371 known distinct prime factors of various Fermat numbers. And we know for sure that 324 Fermat numbers are composite.
And new factors are still being found.
Oh yes, almost every year thanks to projects like Fermat Search and improvements in algorithms and computing power. It's a slow, ongoing process.
Can you give an example of a factorization beyond 5 Tabor dollars?
Sure. $6, which is $264, was factored in the 19th century. It's 274,177 times 672804213107021 Don. Both of those factors are prime.
Wow, even 56 split into two pretty large primes. It's clear why F12 and beyond are so tough.
Indeed. The factors tend to get very large themselves.
Okay, let's shift gears slightly. There's this really surprising connection between Fermat numbers and geometry, isn't there? Constructing polygons.
Yes. The Gauss-Schwanzel theorem is one of the most beautiful results connecting number theory and classical geometry. It answers the ancient Greek question, which regular n-sided polygons can be constructed using only a compass and straight edge?
And Fermat primes are the key.
They are precisely the key. The theorem states that a regular n-gon is constructible if and only if n is either a power of 2, like a square, octagon, etc., or Rn is a power of 2 multiplied by a product of distinct Fermat primes.
So $1 is 2k times P1 times P2 times PSC, where the pile are different Fermat primes.
Exactly. For example, a pentagon is constructible because 5 is fifth $1, a Fermat prime. A 17-gon is constructible because 17 is F2. A triangle is constructible because 3 is the tuple of Ryer.
Yeah.
A hexagon, well, $6, 2 times 3, 3, so yes. A heptagon, 7 sides. No, 7 is not a Fermat prime or a power of 2.
What about a 15-gon? $15 is 3 times 5, 5, and $5.
Yes, 3 and 5 are distinct Fermat primes, so a 15-gon is constructible. Gauss famously constructed the 17-gon when he was just 19, and the 257-gon and 65387-gon are also constructible, in principle.
Because 257, 533, and 65537, $547 are Fermat primes. That's amazing. The existence of these primes dictates what shapes we can draw.
It's quite profound. There's an equivalent condition using Euler's totient function. A regular n-gon is constructible if and only if the power of 2.
And that condition naturally brings in the Fermat primes.
Yes, because POV point for prime P, if P is a Fermat prime 4 plus 1 bol, then quiv, which is a power is 2. And phi of is multiplicative in a way that preserves this power of 2 property for the allowed values of 1 bol.
A really beautiful link. Okay, besides this amazing geometric connection, do Fermat numbers pop up anywhere else? Any practical applications?
They have found some use in pseudorandom number generation, or PRNGs, especially if you need random numbers within a range that's a power of 2.
How does that work?
A common method is the linear congruential generator. You generate a sequence using Vij plus 1 equal A times Vj PAPF. If you choose the modulus ballers to be a Fermat prime and the multiplier dollar to be a primitive root modulo dollar, you can get sequences with very long periods before they repeat.
So using a Fermat prime helps guarantee good statistical properties for the random numbers.
It can, yes. The structure 2/2 plus the con is convenient for certain operations, especially in binary computation. There's also been some theoretical interest in using large Fermat primes in cryptography, but the fact that we know so few large ones makes that rather impractical currently.
Right, limited supply. Now, we've mostly talked about the standard fun-fn plus 11, but there's a generalization too, isn't there?
Yes, the concept has been broadened. We talk about generalized Fermat numbers. One common form is 1FNA BA plus B time, often simplified by taking B $1s, giving 1F most conical line. Here, A is called the base, and it's usually taken to be an even integer greater than 1.
So just replacing the tunac in the original formula with some other base A.
Essentially, yes. If the base A is odd, sometimes people look at A-tex power of 2, called half-generalized Fermat numbers, because A-tex plus an alpha would be even. The overall structure, all-tex power of 2 plus 11 is the key idea.
And are some of these generalized numbers prime?
Oh, absolutely. Finding primes of the form A plus no 1 is an active area of research. In fact, one of Landau's famous unsolved problems from 1912 asks if there are infinitely many primes of the form 1 in mule for 1L1.
So maybe the generalization is where the primes are hiding.
It certainly seems easier to find primes among the generalized Fermat numbers than the original ones based on OBO02. Many of the largest known prime numbers today are actually generalized Fermat primes.
Really? Can you give some examples?
Sure. We know for base 1 or 2, primes only occur, as far as we know, for $100, 1, 2, 3, 4, 2, 8. For base 83, primes 3 to alpha plus no 1 are known for $1, 1, 2, 4, 5, 6 4s. For a $10 pence $2 is prime for $1, 1, 2, 3 TLs. The smallest prime of the form OB02 with 1, 2, 1 is actually 3024 plus 101.
And the largest ones found are huge.
Immense. Many have been found by the Prime Grid Project. As of late 2024, I think the record holder is 124 plus 124 discovered.
No.
Oh, wait, that was an older one. A recent large one is $4 times 511,786,358. That's a generalized form, too.
Yeah.
It has over 8 million digits.
Wow, okay, so generalizing definitely opened up the field for finding these types of primes.
It did. The specific structure still allows for efficient primality tests, similar in spirit to Pepin's test, but generalized, like Lucas-Lammer-Riesel test variations.
Before we wrap up, are there any other sort of related theorems or interesting facts about the original Fermat numbers we should mention?
Yes, a few quick ones, perhaps. There's a theorem that says if you have a prime number of the form $2k plus mon dollar, or tall 1, then the exponent dollar must be a power of 2. So any prime of that form must actually be a Fermat number.
Ah, so it locks the form down to 2 tel mon plus 11.
Exactly. Also, it's known that no Fermat prime can be a Wiefer-Ich prime base 2. Those are primes Peeler model, where $2 were plus mon Peeler, a stronger condition than Fermat's little theorem.
Interesting niche properties.
We already mentioned the form of the divisors, Tulenon, 2 mon plus 11 plus Stier. Luca proved in 2000 that no Fermat number can be a perfect number, nor can it be part of an amicable pair.
So they're kind of mathematically solitary in that sense?
You could say that. And another result by Shirizek, Luca, and Summer from 2002 showed that if you sum the reciprocals of all the prime divisors of all Fermat numbers, that series converges.
Unlike the sum of reciprocals of all primes, which diverges.
Correct. There are also results about how quickly the largest prime factor of 4 done must grow as no increases. And a connection to numbers like sum plus $day dollar, if 1 plus dollar is prime for 122, then no itself must be of the form $2, linking back to Fermat numbers again.
It really seems like they connect to so many different corners of number theory.
They really do. They've been a constant source of questions, challenges, and inspiration for centuries. A truly rich sequence.
Well, this has been an absolutely fascinating deep dive into Fermat numbers, OEIS sequence D000215. We started with that simple formula 2 plus 11 and Fermat's hopeful conjecture.
Which turned out to be wrong quite quickly.
Right. Only the first 5 out to 4 O's are known primes. The rest that we've managed to test are all composite, although factoring them is incredibly difficult.
And leads to huge collaborative efforts like Fermat search.
We saw their unique properties, like being pairwise coprime, leading to a proof of infinite primes, and that unexpected, really beautiful connection to constructing regular polygons.
The Gauss-Wanzel theorem, yes.
And even touching on random numbers and the much broader family of generalized Fermat numbers, where large primes are still being found.
But many fundamental questions about the original sequence remain stubbornly open.
Definitely. So maybe a final thought for you, the listener. Given that we only know 5 Fermat primes and the search has gone on for so long, what would it actually mean if someone someday found a sixth one? Say, if Fi were so much larger, Euro turned out to be prime against all odds. What might that single discovery tell us or force us to reconsider about how primes are distributed or the underlying nature of these numbers?
It would be a monumental discovery.
Something to ponder. If you want to explore more, definitely check out sequence A000215 on the OEIS website and follow the links from there. It's a rabbit hole worth falling down. Thank you so much for joining us and sharing your expertise today.
It was my pleasure entirely. Thank you for having me.